Today, we're diving into the invisible world of software to explore a really fundamental question. How do you manage complexity? How do you build something that's both incredibly powerful and precise when you can't even see it?
Seriously, think about that for a second. An architect, they've got visual blueprints. A mechanical engineer has all these detailed diagrams. But a software engineer, a lot of the time they're working with stuff that's way more abstract. And this very question, it's really at the heart of building the reliable software that, runs our entire world.
And that really gets to the core of the problem. See, it's not just that software is complex, it's that the way we traditionally describe it can make that complexity almost impossible to wrap your head around.
So just look at the difference here. In classical engineering, a formula might be a few lines long, right? Easy to check. But in software, the logic that specifies how a system should work can become a single formula that stretches on for dozens, even hundreds of pages. It's just this linear wall of text, which makes it incredibly difficult for any human being to read it, verify it, and most importantly, spot any errors.
The authors of the paper we're looking at today just hit the nail on the head. They said, the tools of classical math, they just weren't built for the sheer scale of complexity we're dealing with in modern software. Something new was needed.
So what's the answer? Well, it turns out to be an idea that's as elegant as it is powerful, using simple, structured tables to act as the blueprints for all that complex software logic.
And at its core, a software table is just dead simple. You've got your headers, they define the categories or variables, and then you have a grid of cells to hold all the specific logic. You can think of it like an empty template for our blueprint. It's clean, it's organized, and it's just ready to be filled in.
But you should not let that simplicity fool you. This exact structure was used to document the software for the U.S. Navy's A-7E aircraft, a system where just one tiny error could be absolutely catastrophic. So this isn't just some academic theory. It's a proven, battle-tested method for building safer, more reliable systems.
Okay, so we have our blueprint. That's great. But a blueprint is totally useless if you don't know how to read it, right? To really unlock the logic that's hidden inside these tables, we need some kind of map that shows us exactly how the information flows.
So the first landmark on our map is something called a guard. The easiest way to think about a guard is it's the if part of an if-then statement. It's the condition, like if the power is on, or if the pressure drops below a certain level. Those are the guards. And the second landmark, that's the value. And you guessed it, this is the then part of the rule. It's the outcome, the result. Then open the valve, or then sound the alarm. The value defines what actually happens when the conditions set by those guards are met.
And here's where it all just clicks together. A really complex logical rule, one that would normally be this long, confusing line of text, gets completely deconstructed. Each little piece, every condition, every outcome is placed into a very specific cell. Conditions go into guard cells, outcomes go into value cells, and boom, you have a clear visual organization of the logic.
Okay, but that raises a really important question. If you're just looking at a table for the first time, how on earth do you know which parts are the ifs and which are the thens? How do you actually read the logic? Well, you need a key, a legend, you need a map.
And this right here is the paper's central brilliant innovation, the cell connection graph. This graph is literally the map for any table. It visually and formally shows you the flow of information, from the guard components, the conditions, all the way to the value components, the outcomes. For the very first time, there was a universal way to read and understand the logic packed inside any software table.
And the payoff for creating this universal map? It's huge. It actually lets us create a single, unified framework that can describe all kinds of different tables, no matter how they're structured.
And this is the crucial point. Before this research, different tables used in industry often had their own unique, kind of made-up rules. It was really more of an art than a science. This model completely changed that. It turned it into a science by providing one single, consistent, mathematical foundation for all of them.
For example, using this cell connection graph, the model can easily describe a standard, normal table, where the conditions are in the headers and they determine a value inside the grid. And then, the exact same framework can describe an inverted table, where the logic is just flipped. Now the grid has the conditions, and the headers have the outcomes. The model handles it perfectly, no changes needed.
And it doesn't stop there. The model is so robust it can describe even more complex things, like vector tables and the decision tables that are super common across the whole software industry. It's one map, one framework
for all of them. Pretty amazing. So why does all of this formal precision really matter? Well, because at the end of the day, it allows us to build better, safer software for the critical systems that we all rely on every single day.
And I want to be clear, this is not just some academic exercise. This tabular method has been used in some of the most safety-critical applications you could imagine. The shutdown systems for the Darlington Nuclear Generating Station, the avionics for military aircraft, and core systems at the legendary Bell Labs.
Ultimately, the big takeaway here is that having a precise, verifiable, and human-readable blueprint for software is what prevents simple bugs from turning into absolute disasters. It's really about building a foundation of trust in the technology that's all around us.
And that leaves us with a really fascinating question to ponder. By developing these formal ways to manage complexity, we've made our software so much safer. So if we apply this same kind of structured, precise thinking to other complex fields, what seemingly impossible problems might we be able to solve next?